Hi, we're going to continue with Focus 5, and now we're going to talk about how equilibrium responds to different conditions. So you will recognize this as just Le Chatelet's principle. So response to conditions. So the key idea is that when a system at equilibrium is subjected to a disturbance, the composition of the system adjusts so as to tend to minimize the effect of the disturbance. So immediately below that, they just stated as Le Chatelet's principle. When a system at equilibrium is subjected to a disturbance, the composition of the system adjusts so as to tend to minimize the effect. So key idea right off the bat, and now we're just going to think about what kind of disturbances you could create. So when the temperature is raised, the equilibrium composition of an exothermic reaction will tend to shift towards reactants. The equilibrium composition of an endothermic reaction will tend to shift towards products. I like to just think of that as if heat is a reactant, then it's endothermic. And if you raise the temperature, you're adding heat, and so you're going to shift it towards products. If heat's a product in an exothermic process, then you increase the temperature and it's going to adjust by going backwards. And so temperature actually changes the value of the equilibrium constant. The other changes we talk about don't. So temperature impacts the value of the equilibrium constant. And now that we've derived and understand more thermodynamics, this equation comes from looking back at our relationship that said delta G, the change in Gibbs free energy, is equal to negative S, well, I should say dG. I haven't integrated it yet. dt. So if you're holding pressure constant and only changing the temperature, we had this equation, and then you can derive an expression for S in terms of delta H, because you're at equilibrium, and come up with this equation. So we didn't fully derive this, but we know it comes from this expression. When we're only changing temperature and not pressure, Gibbs free energy changes. Gibbs free energy changes, the equilibrium constant changes, and you could use that equation. This just goes through a little more justification of that. If you want to read it, I wouldn't hold you accountable for being able to derive that. This on the top of page 192, really once again, is part of Focus 12. We're looking at the idea of the statistical properties of an equilibrium constant, so we won't worry about that right now. So the first thing we're going to look at is what happens when you compress a reaction. So if you have a reaction vessel and you decrease the volume. So the important thing is if you decrease the volume, you're going to be increasing the pressure. So this is just that equation that relates one equilibrium constant at one temperature to an equilibrium constant at another temperature, and it's the delta H that determines how much they change. So that's what we already have talked about, that it's whether or not the reaction is endothermic or exothermic, whether it goes up or down with temperature, and then how much it goes up or down depends on how big the delta H is. So now if we're talking about compression, it's going to depend on what the stoichiometry is, but for a very easy reaction like 2 moles of gas go to 1 mole of gas, then we start out with an equilibrium constant. Let's say that we decrease the volume by a factor of 2. That means the pressure goes up by a factor of 2. So we're assuming we're holding temperature constant. So our new K, which I really should say now you have a Q, because it has to readjust. So Q is going to be 2 times the old pressure of PC divided by 2 times the old pressure of B and A. And so when you cancel out the 2's, you end up with 1/2. So Q is now really equal to 1/2 of K. And you know, if Q is bigger than K, which way is it going to go in order to reach equilibrium? Yeah, it's going to react forward because it has to get bigger, which also just goes with your common sense that if you increase the pressure, you can alleviate pressure by decreasing the moles of gas. So just a more quantitative way to look at it. So because K is constant, the pressures have to adjust. So have to adjust. Partial pressures to make 1/2 K equal to K. So it has to go back to the value it started at. This is just a very complex way of looking at that. You don't need to be able to follow this through. Just looking at how total pressure impacts the K, and this is for a specific reaction. So once again, it's not very useful because you really have to think of this, as I did here, as the stoichiometry is really going to tell you what happens. If we would have had 2 moles of product and 1 mole of reactant, then we would have ended up with the opposite situation. The K would have been 2 times, or Q would have been 2 times the old K, and then it would have had to adjust in the opposite direction. So you really have to think about it in reference to the stoichiometry. So this particular derivation isn't that useful because it's looking at it in reference to one particular reaction. The next thing is just looking at another way to change the pressure. So another way to change pressure would be to add an inert gas. And so when you started, before you added the inert gas and you were at equilibrium, the total pressure was equal to the sum of the partial pressures for A, B, and C. So I'm looking at that same reaction. And now if I add argon, the total pressure goes up, and my sum over here now has argon in it. So really you can just think of canceling those, and the partial pressures haven't been changed of your reactants. And so the partial pressures don't change, and the reaction therefore doesn't have to adjust in any way. The only other one they talk about in this section is adding a catalyst. A catalyst will change how fast you reach equilibrium, but not the location. So we'll think a lot more about reactions. So Gibbs energy and reaction coordinate. So equilibrium doesn't shift if you add a catalyst and the rate increases. And it's the difference in Gibbs free energy of the reactants and products that determine the equilibrium. So it will impact how quickly you get there, but not where it is. And that is all of that short topic. So Le Chatelet's principle with a little more understanding maybe than in Chem 108, but all the exact same concepts.